All right, here's question 2 and maybe 4 of the 2018 free response questions that are on AP Classrooms. These are international ones there. First one, you have this reaction. Sulfuric acid, salt, making these things. First question, student claims the reaction is a redox reaction. Is the student correct? So remember, redox just means that there is a change in charge from one side to the other. So something has to be going up in charge, something has to be going down in charge. So hydrogen here is a +1 charge, hydrogen still +1 there. Notice you have SO4 here and SO4 here, so it's really going to be the same on both sides, but you can figure out sulfur's charge here. Oxygen's a -2 times 4 is -8, and a +2 there, so sulfur is a +6 here. You have exactly the same thing over there. Chlorine's -1, chlorine -1, sodium +1, sodium +1. It is not a redox reaction. It's actually a double replacement. Precipitate, it's actually a gas. Second one, figure out the mass in grams needed to react with excess H2SO4 to produce 3 grams of HCl. So 3 grams of HCl going to grams of NaCl. So we want to convert this into moles. Mole ratio is 1 to 1. Get to grams of this. Take a look at our answer here. So took the 3 grams of HCl, converted grams into moles. It's a 2 to 2 ratio. 1 mole of NaCl is that many grams. 3 sig figs because we started with 3 sig figs there. It's a pretty simple stoichiometry. Next one. HCl can react with methanol vapor to produce CH3 as represented by the following equation. So here's the reaction. Notice it is a double-sided arrow to equilibrium. It gives us a K value. It is a pretty large K value. 4.7 times 10 to the third power at 400 degrees Kelvin. So we're talking about 4,700, meaning this reaction goes essentially to completion. Going to be a lot more products than there are reactants at the end of the reaction. Remember, it is equilibrium. So equilibrium does not mean equal amounts of things at the end. It means that the forward reaction is happening the same rate as the reverse reaction. Okay, it doesn't mean same number of moles are going back and forth, but the same rate is happening there. So it gives you some information here. It tells us initial pressure, tells us the size of the vessel, and tells us the pressure of HCl. So it tells us 2 pressures there. Does the total pressure in the vessel increase, decrease, remain the same as the equilibrium approach? Justify your answer in terms of the reaction stoichiometry. So if you think about this reaction for a minute, we're starting off with 0.25 atmospheres of this, 0.6 atmospheres of HCl. I'm just getting those numbers from there. Once now at equilibrium, is the pressure going to be more, less, or the same? Well, let's think about this for a minute. We're going from 2 moles of gas to 2 moles of gas. The reaction is going essentially to completion. Okay, so we're going to move a lot in the forward direction, but for every mole of this that's produced, we produce these. For every mole of this, for every mole of this that's used, we get moles of gas over here. Since the moles of gas do not change, the pressure is going to stay the same in this reaction. Let's see what they say here. Pressure remains the same. The reaction stoichiometry shows that 2 moles of gaseous reactants produce 2 moles of gaseous products. Because number of moles of gas does not change, pressure does not change. And those are the only things that cause pressure, remember. Solids, liquids do not. Things that are aqueous do not cause pressure. Second one, considering the value of Kp, remember it's a pretty large Kp, for at the final pressure of HCl after the system inside the vessel reaches equilibrium. So if we think about this for a minute, it's kind of a limiting reactant here. We have 0.25 atmospheres of this, 0.6 atmospheres of HCl. So the reaction is essentially going to completion. Our limiting reactant would be the 0.25 atmospheres of this. Remember, atmospheres for gases are numbers of moles. So we're going to basically use all 0.25 of that. Now, equilibrium means there's always going to be a little bit of that, but it's got a large K, so it's going to be mostly these things. So, and it's telling you, that's why it told you considering the value of K. So our limiting reactant is this. It's a 1-to-1 ratio, meaning 0.6 minus 0.25 would be the amount of HCl left over. So we look here what they did. They did a little ice table. So initially, here's your pressures. There was none of those. They say the value of K is large. So the reaction will proceed to the right until the limiting reactant is essentially used up. Well, there's your limiting reactant. It's all 0.25 atmospheres of that, so it's going to be essentially 0 at the end. 0.6 minus 0.25. This is going to be what's there at the end. You can kind of figure out what these are at that point in time. Third question there. Student claims that the final pressure of CH3OH at equilibrium is very small, but not exactly zero. Do you agree or disagree with the student's claim? So this reaction does essentially go to completion to the right, but it's equilibrium. So some of these are always reacting going back this direction, but there's a very large K value in the forward direction, so not much of these are going back that way, but there's always going to be a little bit of there whenever you're at equilibrium. Okay, tiny little amount. So I would agree, even though we figured the stoichiometry out with that being at zero. Large value of K means the partial pressure of limiting reactant at equilibrium will be extremely small, but some CH3OH molecules must exist for the system to be in dynamic equilibrium. That's how that goes. Next table shows data for CH3CL and CH3Br. So let's look at this data real quick. Molar mass CH3Cl is way less than this because this has got a bromine, this only has a chlorine with it. If you drew a picture of this, you'd have a carbon in the middle, hydrogen's coming off three sides, and a chlorine on one side, and then the bromine would be just the same thing with just a bromine there. Bromine is a much larger atom than chlorine. Notice the dipole moment. Dipole moment means basically how much of a dipole these molecules are. So in comparison, there's not much difference, 1.87, 1.81. They both are dipoles. Not a whole lot of difference, a little bit stronger dipole than this one, but that's not much difference there. Boiling point, this has a much higher boiling point, meaning it must have stronger intermolecular forces than this one. And then this is the heat of vaporization, meaning the number of kilojoules it takes to make 1 mole go from a liquid to a gas. So first thing, identify all the types of intermolecular forces that exist among molecules of CH3Cl. So all of them. So CH3Cl is a dipole, so there'd be dipole-dipole forces, and then there'd be London dispersion forces between those molecules, those two things. In terms of intermolecular force, explain why is the boiling point of CH3Br greater than that of CH3Cl. So why does this have a higher boiling point? Well, they both have dipole-dipole forces, both have dispersion forces, but the dispersion forces in this are larger than the dispersion forces in this because this has got more electrons, meaning it's more polarizable. So the overall intermolecular forces in CH3Br are greater than the intermolecular forces in this, so it's got a higher boiling point. Let's take a look at that. See what they say here. It's always good to look at their wording. Electron cloud in CH3Br is larger and more polarizable, meaning it can become kind of a dipole, than that of CH3Cl. As a result, the London dispersion forces are stronger in CH3Br compared to those in CH3Cl. Consequently, the boiling point of CH3Br is higher than that of CH3Cl. Last question here. A 2 milliliter sealed glass vial, so that's pretty small, 2 milliliters, containing a 1 gram sample of CH3Cl is stored in a freezer at this temperature. Figure out the pressure of the vial at 298 degrees Kelvin, assuming all of it vaporizes. So it is a gas now. It was, I'm assuming liquid here, maybe frozen, probably liquid there, and is now gas right here. So we are going to do a little PV on RT using this temperature. There's our volume. Looking for pressure. We need to turn this into moles. Be careful, this is in milliliters, needs to be in liters, so it'd be 0.002 liters. That's in Kelvin, that's good. This just needs to be in moles. So PV on RT it. They got their grams into moles, plug the moles in. 242 atmospheres to 3 sig figs, because there were 3 sig figs in this. Remember, the zeros at the front do not count. Explain why it would be unsafe to remove the vial from the freezer and leave it on a lab bench at 298 degrees Kelvin. So they have this vial at 233 degrees Kelvin. Excuse me, my voice is cracking. Or it just sounded that way on the video. If they heat that from 233 to 298, notice what that pressure was. What was that pressure? 242 atmospheres of pressure. And 1 atmosphere is basically where we're at right now. More than likely that vial would explode. At room temperature, the liquid will vaporize. Consequently, the glass vial may not be strong enough to withstand the increase in pressure. There's question 2. We will stop this right here. Have a great day.